Greetings all. So till now we have studied about the heat generation case in case of plane wall when both the sides are maintained at different temperatures, as well as for the case when both the sides are maintained at same temperature. It means that on both the sides similar kind of fluid is there. Now moving forward, we will see the case when heat generation in case of solid cylinder, and surface of the cylinder is maintained at some constant temperature by the fluid uh, which is present outside the surface. Okay, and heat is generating inside the cylinder at the uniform rate. So let me write this, that heat generation in case of solid cylinders. This is the model for the real life situations, like when electric wire carries electric current, heat is generated inside it because of the current flowing through it. So if we assume that current is flowing in such a way that heat is generating a uniform rate inside the wire, then that case can be modeled as the heat generation in case of solid cylinder. All right. So, and surface maintained at constant temperature. So this is the third case we are seeing. We have seen two cases already in the previous lectures. So again, our approach will be like first we have to define the problem, that this is the cylinder. Okay, and this is the side view and this is the top view, and outside the cylinder there is some fluid with characteristics of free stream temperature as T infinity and heat transfer coefficient as H, and because of that fluid the generated heat will be coming out of the cylinder and some temperature will be maintained on the surface at every height. We are assuming that there is no variation of temperature with height, means at every height same surface temperature is there, which is nothing but Ts, and Ts must be, and Ts is not equal to T infinity. Mind that if Ts is equal to T infinity, then heat transfer will not occur. For heat transfer to take place, temperature difference must be there. All right. So Ts, if it is generating inside the cylinder, then Ts will be greater than T infinity. Then heat will flow out of the cylinder, right? So we have to find in this case that how temperature profile will look like inside the cylinder, right? As this is a case of symmetry, the maximum temperature will be at center. Okay, so temperature profile will be such that maximum temperature will be at center, right, because of symmetry. Okay, but you have to find that how temperature will vary with R. All right, so again, for solving this problem we have to start with the governing heat equation. All right, so for cylinders we have seen that this is the general equation for one dimensional case, right? 1 by A del R by R times A del T by del R plus QG. If you want to write the general equation, you can put thermoconductivity also inside, plus QG. QG is volumetric heat generation in watt per meter cube. All right, and the right hand side is unsteady term. Sorry, this is, as we have taken k inside, we should write like rho Cp times del T by del T. Rho is density of the material and Cp is the specific heat of the material of the cylinder. Alright, so we are assuming that the material is homogeneous and isotropic, so K can come out, but A is function of R here for the case of cylinder. Alright, A is that area which is experienced by the heat flow direction. Alright, there is nothing but 2 pi times R. At any radius we have area as 2 pi R, so area is function of R. So if we write in the above equation, we can get this, and we can take K as constant because material is homogeneous and isotropic. Okay, and also we are assuming that this is case of steady state, right, and one dimensional. So inside this bracket we have 2 pi R, 2 pi will cancel from outside and inside. Alright, let me write that A is 2 pi R, then K will come out, and A is 2 pi R again, del T by del R plus Qg by K equal to 0. 2 pi will cancel out, we will get 1 by R del R by R times del T by R time plus R time del T by del R, Qg by K equals to 0. So we have to find the solution for this equation. One more thing, since we are assuming only one dimensional heat flow, that is only radial direction, right? So we can write these partial derivatives as ordinary derivatives d, right? So it is second order differential equation. All right, ordinary differential equation. Now we have to integrate it twice to get the temperature profile. So if we integrate for the first time, we can get R times dt by dr minus qg r square by 2k plus c1, right? As we have seen above, that at the center temperature will be maximum. It means slope of temperature will be 0 at the center, right? So and since it is a second order equation, second order ODE, we need two boundary conditions to solve this equation. All right, so the first boundary condition is that R is equal to 0, means center the temperature is maximum, means slope is 0. So we can get from here C1 as 0. So if we plug this C1 value here, we can get del dt by dr is equal to minus qr by 2k. All right, so we can see from this that temperature gradient is function of R itself. In the steady state cases, when there was no heat generation, we saw that at any position, the whatever heat is coming in, that same heat will be going out. But this is not true for the case of heat generation. let me give you the example. If we see the top view of the cylinder like this, and if we are at 2 radiuses, let's say, right? So in the case of steady state, when there is no heat generation, so whatever heat that is coming in, the same heat will go out. How? And if it is steady state, let's write the energy equation: Q in minus Q out plus whatever heat will be generating between these two surfaces. Q stored, that is the unsteady part. Okay, so for the case when there is no heat generation, this term, and for steady state this term will be knocked out, and only Q in will be equal to Q out. That is when there is no heat generation and steady state. But when there is heat generation, so in that case Q in will not be same as Q out between any two surfaces of the cylinder. Alright, inside surfaces between any two radiuses, right? So that was the thing that I want to point out here. Minus Q gen, this term is coming extra. So it is case of internal heat generation and steady. Okay, so this is thing which we have derived here. So we have to integrate it one more time. So integrate it, we can get Ts minus Qg r squared divided by 4k plus C2. And the other boundary condition is surface temperature at R is equal to capital R. So boundary condition number 2 is at R is equal to capital R means surface, TS, temperature is at TS. So plug in that value, TS we can get, C2 we can get as TS plus Qg capital R square divided by 4k. Okay, and plug this value in second equation, we can get the temperature as a function of R as Ts plus Qg r square divided by 4k minus Qg small r square divided by 4k. We can take Ts on left hand side, T of R minus Ts, and Qg r square if we take out as common, we can write like this. So T varies as function of R square, so it is the equation of parabola. So inside the cylinder, temperature profile from the radius to surface will look like a parabolic in shape. Alright. Right. And if we want to find the maximum temperature, we can put at R equal to 0, we can get the maximum temperature as T max minus Ts as Qg r square divided by 4k. This term will go to 0. So this term is T max minus Tx. So we can further write the above equation as T minus Ts divided by T max minus Ts equal to 1 minus small r square by capital R square. Okay.